Okay, hi guys, welcome to your first day of Course 1 tutoring. As I said before, my name is GT, but you can call me T. So let's get started with Chapter 1. So our first unit is going to be numerical expressions and factors. So what you'll learn in our first section of this chapter is adding and subtracting whole numbers, multiplying whole numbers, dividing whole numbers but with no remainders. And with every section, you'll be learning some real life applications about how you would use this type of math in real life. So our first example here is you have this graph here. So our first question is, what was the total attendance for the art festival? And the second one is the increase in attendance from the first day, which is here, to the second day, which is here. The third question is, how did this increase from this day, the second day, to the third day? And the fourth one is, what was the increase from this day to this day? So basically, this is just basic addition or subtraction. So how we would go about this is, do you guys want to try it first? I'll give you some time to try it by yourselves, and then I'll give you a little explanation in about 10 seconds. Okay, so how you'd go about this is first, we need the total attendance. And for the total attendance, we need to add all of the people from each day of the art festival together so that we can get the total amount of people for the whole day. So that would be adding this number plus this number plus this number, which is 2,570 plus 3,145 plus 3,876. And when you add all of these up together, we would get a total of 9,591 people. For the second one, we have to find the difference of day 1 and day 2. So what we do is we subtract day 2, which is 3,145, and subtract day 1 from it, which is 2,570. And when we do this, we get a difference of 575 people. So the third one is we're finding the difference, or we're subtracting from day 2 to day 3 day 3, and we're subtracting day 2 from it. So we subtract this number from this number, 3,876, from 3,145, and we would get 731 people. And then the fourth one, we find the increase in attendance from day 1 to day 3. So what we can do is we can subtract day 1, the number of people, from day 3. And that would basically be 3,876. So, okay, someone's coming. And you subtract 2,574 from it. And this would give us 1,306 people. So these are the solutions here to each problem. Okay, here's our next example, which is a real life application. So let's say, I'm sure you guys have seen school lunch or have bought school lunch or anything. And maybe this would have been you, but I'm not really sure. So a school lunch contains 12 chicken nuggets, and there are 95 students who buy the lunch. What we're trying to find out is, what is the total number of chicken nuggets served? And if the meal was half, meaning if there was 6 chicken nuggets, how much chicken nuggets in total would be served? So I'll give you some time to think about that. Okay, so here's how we go about this. This is basic multiplication. So because we know that there are 12 chicken nuggets and that 95 people are buying a meal of 12 chicken nuggets. So gives us 95 groups of 12 chicken nuggets. So this means we have to try to find the product of 95 and 12. So that would give us 1,140 chicken nuggets. The second one, if the meal is being halved, that means there's 6 chicken nuggets in each meal, and there's still 95 students buying that meal. So we know that we have to do 95 groups of 6 chicken nuggets, meaning multiply, and this would give us 570 chicken nuggets. And our next real-life application problem is there's a 301-foot-high swing at an amusement park. Amusement parks are very fun, and it can take 64 people on each ride. 8,983 rides the swing today, but at the last ride, the ride was full. So we're trying to figure out how many rides were given in total and how many people were on the last ride. So to find the rides, we divide the amount of rides by the people, and to find out how many were on the last rides, we just use the remainder because that gives us how much people were remaining. Okay, so the first step we do is we try to find the quotient of 8,983 and 64 because there's 64 people on each ride. This would give us 140 remainder 23. This means that there's 140 rides and there's one extra ride to account for this remainder of people. Because the remainder is 23, that means that there were 23 people on the last ride, which answers our second question right here. So these two are the solutions, that there were a total of 141 rides, and on the last ride there were 23 people. Now we're on to our next section here, which is 1.2 powers and exponents. In this section, what you'll learn is writing expressions as powers, finding the value of powers, identifying perfect squares, and as I've said before, real-life application problems. Okay, so as we go through course 1, you'll see these using defined terms as well as key ideas. And as we go through, you'll see more of these defined terms and more of these key ideas as it starts being more new content given to you.
సరే కూర్చో స్ట్రైట్ కూర్చొని విను.
Okay, so our first term is a power. A power is a product of repeated factors. So this would be like 4 times 4 times 4, or if you're using a variable, it can be like a times a times a, or something like that. Our next defined term is a base. A base is the repeated factor, but not the product of it. So a base would be 4. Let's say 4 is raised to the power of 2. This means that 4 is the base and 2 would be the exponent, bringing us to our next term, exponent. An exponent is what indicates the number of times the base was used as a factor. So an example of this would be, let's say 2 is the base and 3 was the exponent. This means that 2 is being used as the factor 3 times, and this would be the same as saying 2 times 2 times 2. And our next term are perfect squares. Perfect squares are a square of a whole number. So let's say 2 times 2 is equal to 4. This means that the perfect square of 4 would be 2. Or the perfect square of 2 would be 4. And so here are some diagrams to help you better understand. If 3 here is the base, 4 is the exponent, and the whole thing itself would be referred to as a power. This is how it's like written out as. If you were to write it out, it would be 3 used as a factor 4 times, which would be 3 times 3 times 3 times 3. And 7 to the power of 2, which is the same thing as 7 times 7, is equal to 49, meaning that 49 is a perfect square of 7. Now, our first example is to write each product as a power. So here we have 4 times 4 times 4 times 4 times 4 times 4. So we're going to write this as a power, meaning as an exponent, like with an exponent above it. So we have 4 here 6 times, meaning that our exponent is going to be a 6. And as we can see here, 4 is our base. And then this one, we have 15 multiplied 4 times. So we know 15 is our base here, and it's raised 4 times, meaning 4 is our exponent. So because 4 is used 6 times, this gives us 4 to the power of 6. And because 15 is used 4 times, this would give us 15 to the power of 4. Therefore, our solutions would be 4 to the power of 6 and 15 to the power of 4. Now, here we're trying to find the value of each power. So first we have 6 to the power of 2, and we have 4 to the power of 3. So if 6 times 2 is equal to 6 times 6, and 4 to the power of 3 is equal to 4 times 4 times 4, you have to evaluate those two, meaning you have to multiply out. So I'll give you some time to try to figure this out by yourself. Okay, so here's our explanation. 6 to the power of 2 is equal to 6 times 6, and 6 times 6 is 36. 4 to the power of 3 means that the base of 4 is multiplied by itself 3 times, which means 4 times 4 times 4. And 4 times 4 is 16. 16, so these two are 16, and 16 times 4 is equal to 64. This gives us our solutions of 36 and 64. Next is our real-life application problem. We have a checkered coaster right here, and it's a square with a side length of 7 squares. If it's a square, we know that one side is 7, and since it's squared, the other side is also 7. So what we're trying to find is the area of the coaster. Because we're trying to find the area, this is equivalent to 7 squares because there's 7 here and 7 here. And 7 squared is equal to 7 times 7 multiplied out. The second thing we're trying to find is if our length were 4 squares on each side. So that would be just this little portion right here. So if this was the whole coaster right here, what would the area be? So for the first question, we have 7 squares on each side, meaning 7 squares to the power of 2. And this is equal to 7 times 7, as I said before, which is a total of 49 squares. You could have also counted them out, but that would be much more difficult to do. So, 2, if each were 4 squares, like just this little portion right here, to the power of 2, this would give us 16 squares. Again, you could have counted it out, but it's much easier to use exponents than counting it out, as this is more tedious and will take more time. So here are solutions. For the first problem, our solution was 49 squares, and for the second problem, our solution was 16 squares. Okay, now we're almost halfway there, guys, so don't worry about it. So this is our third section, which is order of operations. Okay, so what you'll learn in this is using order of operations, using order of operations with exponents, which is what we learned in our previous section, and complex order of operations, which is having multiple operations in one expression. And last but not least, our real life application. So let's go. Okay, so we have some defined terms for this section. Our first one is a numerical expression. A numerical expression is an expression containing only numbers and operations. So it doesn't have any variables in it at all. Our next term is to evaluate. Evaluating is when you use the order of operations, which we'll learn today, to find the value of a numerical expression, which is here, meaning an expression which does not have any variables. Next is our order of operations, and this is going to be very important for any math in the future. I guarantee you guys will be using this a lot. So an order of operations is an order in which you perform operations when evaluating expressions with more than one operation. So I'll just explain the order of operations to you guys real quick. So the first step of the order of operations is parentheses. You guys might want to write this down if you don't know this already. So if you have parentheses, like these things or brackets around it, that means you do that part first. That's the first thing you do. The second thing you do in order of operations are exponents. So if you see an exponent, you would be solving that out first. Next, you multiply and divide. So any multiplication or division, you do those first, and then you add and subtract after you multiply and divide. So this is an example of a numerical expression. It doesn't have any variables in it, and it's just a number and operations. So to evaluate this numerical expression right here is the same as performing the multiplication before the addition, which means using the order of operations, you know that you have to multiply before you add. So 5 plus 2 times 3 is equal to 5 plus these multiplied out first, which is 6, and that gives us 11. So let's get started with our examples. Our first example is 10 times 4 divided by the quantity. If you see these parentheses, you can refer to these as a quantity of 2 times 4 plus 3. So the first thing I want you to do is determine in which order you would evaluate this expression. And then after you've determined that, you evaluate the expression. Okay, so to determine what order we evaluate the expression. So I explained before that first you have to solve out the parentheses using PEMDAS order, which is parentheses, exponents, multiplication, division, addition, and then subtraction. So since we have parentheses here, we have 2 times 4, and this gives us 8. So now we have 10 times 4 divided by 8 plus 3. 10 times 4 is what we do next because it's multiplication. 10 times 4 is equal to 40. So now we have 40 divided by 8 plus 3. So 40 divided by 8 is equal to 5. And we know that's the next thing we do because in PEMDAS order, division is what comes next after multiplication. And then last but not least, we add 3, which gives us a total of 8. So what we did here is first we did parentheses, then we did our multiplication operations, then we divided and then added. And our solution for the evaluation was 8. Okay, so, okay, so our next one is this, and I guess the explanation and solutions are shown here for some reason. So in what order would we evaluate this, and what is the expression that is evaluated? So first we know we have to do PEMDAS order, which is we first solve this out, 8 plus 1, which is 9, and then this exponent, 3 to the power of 2, which is equal to 3 times 3, and which is also 9. So now we have 10 minus 5 times 9 divided by 9. So because we know that next is multiplication, we know we have to do 5 multiplied by 9. So 5 multiplied by 9 is 45. So now we have 10 minus 45 divided by 9. So we know we do division next. So we have 45 divided by 9 here, which is 5. And this gives us 10 minus 5, which is 5. So the order in which we did it was parentheses, our exponent right here, multiplication, division, and then we subtracted all of it from 5. And this gave us 5. Okay, so our next section here is prime factorization. This is also another really important thing for the future, and it'll help you be able to do more problems when they have big numbers in them. So what we'll learn here is finding factor pairs, writing prime factorization, and using a prime factorization, such as like a factorization tree or multiple pairs. We have defined terms here. So our first defined term is a factor pair. A factor pair is when you have 2 whole numbers multiplied together to get a product. So this would be like 2 times 3 is equal to 6. 2 and 3 are factor pairs to make 6. Our second term is prime factorization. This is a composite number written as the product of its prime factors. For example, if you have 6 written as its prime factors, this would be 2 times 3. So that's the prime factorization of 6. Next is a factor tree. A factor tree is a diagram that shows the prime factorization thoroughly of a number. So it looks like kind of a tree with the number at the top and little branches with each factor until you're completely factored out and you've reached the prime factors. So here's some things to help better understand. Because 2 times 5 is equal to 10, the pair 2 and 5 are the factor pairs of 10. This is the prime factorization of 60. See, none of these can be factored further, therefore they're the prime factors of this number. And this would be the factor tree of 60 and how you would write it out. You see that these can't be factored further, and these would be the prime factors since you can't divide them further. So our first example here is find the prime factorization of 1575 and then find the greatest perfect square. As you can see, we have a factor tree right here. So the prime factorization is already given to us here, the one circled in red. So the factorization is 5 times 5, 7, 3, 3. Those are the prime factors. And then 2, find the greatest perfect square. So the factorization shows 3 perfect square factors besides 1. These factors are 5, 7, and 3. So our solutions are that this number is equal to 5 times 5 times 7 times 3 times 3. And also, if we multiply 5 times 7 times 3, wait, no. Okay, so these would, 5 times 7 times 3 is equal to 225. So that's the greatest perfect square. Also, questions I'll answer at the last 15 minutes of class. So if you have any questions, just save it for me and ask it at the last 15 minutes, and I'll be sure to go through anything you guys ask. So here's a real life application problem. The brass section of a small marching band has 15 members, and each row has an equal amount of members. So if you want, you guys can try to draw a diagram here. So we're trying to find the possible number of arrangements and how many people are in each arrangement. So first, we see that the number of factors is equal to the number of arrangements. So since there are 4 factors, there are 4 arrangements that we can do. The possible factor groups is equal to the number of people in each arrangement. So we have 4 possible arrangements because 15, has 4 factors. And this gives us 4 possible arrangements. So our arrangements, if you think about it, we have 30 rows of 1, 5 rows of 3, and 3 rows of 5. So 1 row of 30, 30 rows of 1, 5 rows of 3, and 3 rows of 5. So now we're on to our second to last section of our first chapter here, which is the greatest common factor. What we'll learn here is finding the greatest common factor using a list of factors, which is kind of what we talked about in our previous section. Finding the greatest common factor using prime factorization. Finding 2 numbers given the greatest common factor, and of course, our real life applications. So we have some defined terms here too. A Venn diagram. So a Venn diagram is a diagram that uses circles to describe relationships between 2 or more sets. And I'm sure you've seen a Venn diagram before. It's when you have like 2 circles and then there's a little section where they both overlap in the middle. So common factors are factors that are shared by 2 or more numbers. So let's say you have 12 and 6. Some common factors of that would be 6, 3, 2, And then our greatest common factor is what, like our key idea for this section. Our greatest common factors are factors of 2 or more numbers that, well, as the name says, the greatest common factor. So this is how a Venn diagram looks like. I'm sure you've seen it before. We have club A, club B, and then this intersection is both clubs. So 2 is a common factor of 8 and 10 because it's a factor of both of the numbers. Okay, so the common factors of 12 and 20 are 1, 2, and 4. So the greatest common factor of 12 and 20 is 4 because as you see, we have 1 and 2, but that's not the greatest one. The greatest one is 4. So let's get started on our examples. Fun, right? Okay, so there are two numbers, 20 and 30. Okay, so what we're doing is we're going to list the factors for each number, 20 and 30, and then we're going to determine the greatest common factor of the two numbers. So I'll give you some time to kind of think about this by yourself and maybe list the factors down. Okay, so we have these two numbers, 20 and 30. So we find both the factors of the number, and then the greatest common factor is the greatest factor present in both. So we have 20 here. So the factors of 20 is 1, 2, 4, 5, and 10, because these are all the numbers that you can divide 20 by. Like you can divide 20 by 1, 2, 4, 5, and 10. So therefore, these are the factors of 20. And then 30, the factors are 1, 2, 3, 5, 6, and 10. As you can see, we have common factors. 1's a common factor, 2's a common factor, 5's a common factor, and 10 is a common factor. But we're just trying to find the greatest common factor, so that would be 10, which gives us our answer to number 2. So we have 4 pairs of numbers this time. 10 and 15 are paired together. 30 and 60 are paired together. 21 and 45 is paired together. 45. Oh. No, 15 is not a factor of 20 because 20 can't be divided by 15 without a remainder. So therefore, the greatest common factor is only going to be 10. And if you have any more, yeah, we know 15 is a factor of 30. There are like infinite factors, but we've reached our greatest common factor here, and there are no more factors of 20, so we know that, except of course 20 itself, so we know that we can stop here without having to factor 30 even more. Okay, so there are 4 pairs of numbers, 10 and 15, 30 and 60, 21 and 45, and 45 and 75. So we're trying to determine which pairs of these 4 pairs has the greatest common factor of 50. And then we're trying to figure out which ones have a greatest common factor of 20. So basically, we have to factor all of these 4 pairs out to find what common factors they have. So before we start doing that, we can eliminate the first and third pair. The first and the third pair, because we see that you see how these two, we're trying to find the greatest common factor of 15. Well, 10 is a smaller number than 15, so you can't divide 10 by 15. And we know that 21 can't be divided by 15 either without getting a remainder. So we can just eliminate these 2 pairs right here. So all pairs but this, and then for the second one, all pairs but the second can be eliminated to get this pair 30 and 60, because these are the only ones that can be divided by 20. And you know just by looking at it that these all would have a remainder, but this pair wouldn't. So our solution here is this pair 45 and 75. And then for the second one, our solution is this pair 30 and 60. Okay, now for our real life application problem. We have a shopping list here for someone trying to make gift bags. I don't know if you guys have made gift bags before, but you try to find some stuff to put into them. So we have 18 bottles of nail polish, 24 pairs of earrings, and 42 hair bows, maybe for like a return gift thing or something. So what we're trying to find is how many identical gift bags can we make with having the least possible numbers of gift and without having any leftovers. So what would we do is we have to find the GCF, or greatest common factor, of all the bag's items. So 18, 24, and 42. When we factor these out, we get a greatest common factor of 6. So when 6 is equally distributed, we know that we can make 6 gift bags, because we can distribute 6 of these each, like 6 gift bags, we can distribute all of these into equally. For example, like 3 of these in one, and 4 of these in one, and then 7 of these in one. And then for our last section of our first chapter and of this first session of tutoring is least common multiple. So we talked about greatest common factors, which is the factors of that number, or what it can be divided by. But now least common factor is what you can multiply that number by and get the least number by multiplying that number. So what we will learn is finding the least common multiple using the list of multiples, finding the least common multiple using prime factorization, finding the least common multiple of 3 numbers, and of course, our real life application, how this would be used in a real life situation. So, our defined terms. Common multiples. Common multiples are multiples that are shared by 2 or more numbers. A least common multiple is the least of these. So least common multiple is basically the least common multiple of both the numbers. So we have the multiples, and the smallest value is our least common multiple. So for example, multiples of 4 would be 4, 8, 12, 16, 20, 24, and these can go on forever, but we'll just stop here. And multiples of 6, 6, 12, 18, 24, 30, 36. As you can see, it's all going by 6s, and these are multiples of that number. The first 2 common multiples of these 2 numbers are, as you can see here, is 12. Therefore, this is the least common multiple. So here's our first example. So our first pair of numbers are 2 and 3. We're creating a list of 6 multiples for each number. And then the second thing we're trying to find is, using this list of multiples, what is the least common multiple? So for 2, we have 2, 4, 6, 8, 10, and 12. So that's our first 6 multiples for 2. And for 3, we have 3, 6, 9, 12, 18, and 21. So that's our first 6 multiples for this. So gradually list the values that 2 and 3 factors of these factors of 2 and 3 until reaching the 6 values. And then second, we find the first common multiple in the 2 list, which is 6. So our solution here is multiples of 2 are 2, 4, 6, 8, 10, and 12. And then 3, 3, 6, 9, 12, 15 should be here, but it's not for some reason, 18, and 21. So as you can see here, our least common multiple that both of these share is 6. Therefore, our least common multiple, our second question here, is 6. Okay. So we have 3 numbers this time, 4, 15, and 18. So we're just going to write the prime factorization of each factor and circle each factor where it appears the greatest number of times. Using what we find in the first question, we're going to find the least common multiple of the 3 numbers. So to solve the first one, we can highlight the unique factors after doing the LCMs and finding the multiples of each one that appear the most. Overall, this would be 2, 5, and 3. Then we can use these to find the least common multiple. So as you can see, when we factor these out, we get 2 times 2. For 15, we get 3 times 5. And for 18, we get 2 times 3 times 3. So we know that for this one, we can highlight 2 because it's the only one that's unique to 4. So for 15, we have 3 and we have 5. But as you can see, 3 isn't unique to 15 because it appears in 18 also. So this is why we highlight only 5. And for 3, we know 2 we have already highlighted in 4, so we can just highlight these 2 3s here. So because of this, our unique factors give us 2 times 2 times 5 times 3 times 3. And oops, this would give us a total of 180, which means that 180 is the least common multiple of these 3 numbers. Okay, now for our real-life application problem. A walk sign changes every 30 seconds. On another part of town, it changes every 40 seconds. We're trying to find when will both lights change at the same time. To do this, we find the least common multiples of both of the numbers. So what we can do is we find the multiples of 30 and 40. When we do this, we find that the least common multiple is the answer of 120 seconds. And since there's 60 seconds in 1 minute, this can be converted to 2 minutes. So our solution here is after 2 minutes. This is because the multiples of 30 can be 30, 60, 90, and 120. And the multiples of 40 can be 40, 80, 120. And as you can see, both of them have 120, and it's the least value that appears in both of these numbers. Therefore, we know that they change at the same time every 2 minutes. Okay, so we've finished our first chapter and we have 15 minutes left. So if you guys have any questions, feel free to unmute or type it in the chat box and I can answer the question that you guys asked. So you guys can unmute yourselves now. It's completely fine to unmute and just ask anything you guys want. Okay, so Nidhi asked, what is a perfect square? A perfect square is basically, here, let me go back here to show you. Let me just do this. So this was in our second section. So basically, a perfect square is a square of any whole number. So okay, let me answer this question first. So 1 times 1 is equal to 1. And then it's basically a perfect square is a number times itself. And the value that it makes is its perfect square. So let's say we have 4. 4 times 4 is equal to 16, meaning that 16 is the perfect square of 4. If we have 5, 5 times 5 is equal to 25, which means that 25 is the perfect square of 5. So a perfect square is basically when you have a base number, like any whole number, that is multiplied by itself, the value that multiplying those numbers make is what a perfect square is. Okay, so second question, what is a factorization? A factorization is, let's say you have a number 4. Let me see if I can write this out somewhere. Yeah, I don't think I can write it out. So if we have a number, let's say we have a number 4. The factors of 4 can be 1, 2, or 4 itself. So let's see. Okay, so if we have 4, does that help you understand it? Let me see if I can write it out somewhere. I can try doing it with this thing. So if we have 4, 4 can be separated into 2 times 2, and each one of those can be separated into 1 times 2. So our factors of 4 would be 1 times 2 times 2 times 1, since those can't be divided further. So that's how you factorize something. Okay. Okay, so basically when you factorize something, you have that number and you have everything that that number is divisible by until it can't be divided further. And when you can't divide it further, those are all the prime factors of that number. Okay, so does anyone else have any other questions? No? Okay, so if you guys don't have any other questions, I'm gonna try to explain to you how our...
I have just one thing.
Can you go faster next time? I mean, can you go slower next time? Like
Yeah.
when you're doing the problems, because I don't have time to do it.
Yeah,
I
of
don't have time
course.
to do the example problems.
Okay, yeah, sure. Just let me know in the chat box how much, if you need more time or if I'm going too fast.
Okay.
Okay.
Thank you. Say thank you.
Okay, so if nobody has any other questions, I can teach you guys like how the homework is gonna go. So I'm gonna, okay, let me just stop presenting right here. Okay, so I'm just gonna like, so you guys are all on the classroom, right? Yeah. So I'm assuming you guys are all in the classroom. So on the classroom, I'm going to be posting some assignments, like some practice problems to review what we learned in this chapter. And they're not like hard, they're just like a few problems to kind of refresh yourself on what we learned and to better absorb the information. So these practice problems are basically everything we've learned so far, not too much. And they're going to be due in a week. And if you have any questions on those, we have me and the other tutor, we have our emails on the document. So if you have any questions, feel free to email us at any time with any questions you have. If you want, I'll post the assignment right now so you guys can look over it right now. And if you have any questions, you can just tell me on this call itself. So does anyone have...
Do we have another class tomorrow at the same time?
Yes, you guys do. This is going to be a chapter 2 class for chapter 2, and it's not going to be me teaching it. It's going to be one of my friends teaching it. So you will have an assignment for that one too, but it's going to be due in a week.
So when is the homework due that you're going to give us?
It's going to be due in a week, so like before our next session starts. And don't worry, It's not like hard or anything. It's just a review.
So it's only on Saturdays and Sundays?
Yeah, your tutoring sessions are only on Saturdays and Sundays. Okay, so I'm gonna post your first assignment, and with each assignment, I'll give you guys an answer key so you can you can check your answers with the answer key too.
How many assignments are we going to get?
So you're gonna get one assignment for each chapter or one for each session, and that's pretty much it. Okay, sometimes at the last 15 minutes, you may be given like a small quiz, but that's pretty rare. Probably won't happen that much.
Do we have to click on the same link that we did to get into this
Yes.
call?
Same link. The same link. Yeah. So does anyone have any other questions? Okay, so I'll be.
Are you gonna post the assignments right now?
Yeah, I'll post them right now.
Oh, okay.
Chapter 1 home. So does anyone have any questions on what we learned or any suggestions for what I can do to help you better understand the curriculum next time? No, nothing at all. Okay, that's fine then.
I have a question.
Yeah.
About the assignment that you're gonna post for us, like as homework or something.
Yeah.
When are you gonna post it?
I'm gonna post it right now. In the next couple of minutes, you should probably see it on there.
Oh, okay. Thank you.
And if you want, you can do it on a piece of paper, and you can take a picture of it and just upload it onto Google Classroom. And with each assignment, I'll be posting an answer key too, so you guys can check back.
Are we gonna get graded? I'm
not gonna grade you on it. It's just so that you can better understand it for yourself.
Okay.
Okay, so you should be seeing it now. Do you guys see the assignment?
Are we gonna get a new assignment every day?
Not every day, so only the days which you have a session, which would be today and Sunday, you'll get an assignment on what you guys have learned.
Oh, so just 2 assignments then?
Yeah, per week. So 1 assignment today and 1 tomorrow. And they're pretty easy, pretty straightforward. They're just review on what you've learned, just so you can better understand. And remember, if you have questions on any of the assignments, feel free to email us.
Okay, thank you.
Yeah, so that's pretty much it. And yeah. So does anyone else have any questions on anything at all to do with the curriculum, what you're going to learn coming soon, how it's going to work? Because if not, then I guess we're done and see you guys next week.
Wait, so tomorrow at are we gonna have the same teacher every week?
So basically, I'll be the one teaching on Saturdays, and my friend will be the one teaching on Sundays. And it's going to be chapter 1, 2, 3, 4. So each day, on let's say Saturday, you learn chapter 1. Tomorrow, you're going to be going over chapter 2, and then next week, chapter 3.
Oh, okay.
Anything else, you guys? No? Okay, then I guess that's it, and see you guys later. You guys can leave the meeting if you want to. And have a great day.
Bye.
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 Thank you. Bye.
Bye.